Okay. Anyway, as I was saying, this is the last notes. Tomorrow is the R problems. Monday is the team test. Tuesday is the FRQ whiteboard day, and the T problems are the homework. And then the test is on Friday. Does that make sense to everybody? Okay. Um, Now last notes, sampling distribution of a difference between two means. I want you to get your yellow sheets and try to find the center and spread for the sampling distribution of X bar 1 minus X bar 2. Try to see if you can find that yourself before you write it in. Okay, let's see if you found it. It's right here. This is the center. This is the spread. Okay, so we're going to write that stuff in our notes. So center, mean of X bar 1 minus X bar 2 is the mean of the first one minus the mean of the second one. Again, you can find that formula right here. What does that mean for us? It means that we can subtract means. We knew we could subtract means. We can add and subtract means all we like. Can we add and subtract standard deviations? No. So this formula takes that into account. It changes them into variances, then combines them, and then square roots it, just like you would expect. Okay, however, what do we know about a condition for standard deviation for all of these? All of chapter 7 has the same condition for standard deviation. 10%. Okay, so if the 10% condition is met for both samples. And remember, we did one like this before where it was p-hat and it was annoying because you have to check twice. So it's not a big deal, but you do have to check twice. Okay, and the formula is that. I don't know why one of my standard deviations is skinny, but it's okay. Is it okay? I might need to fix it. Okay, really carefully, just want to pause here real quick. These are squares, these are labels. These are squares, these are labels. And that should make sense because you have to convert it to variance before you can add it and then square root it to get it back to standard deviation anyway. But just for making sure you write this down nicely, these guys are squares. And then this is standard deviation 1 and standard deviation 2. Am I making more of that than it is? Okay. Just be careful when you write it on your note card. All right, now shape. What do we learn about shape on Tuesday? It was very important. I did a lot of like waving my arms around and there was stuff up there on the screen and so yes. Okay. So it gets less variable and more normal when you're talking about averages. But what is the biggest factor for shape? Sample size. Yes. Okay. So on Tuesday, we said if the shape of the population is normal, then the shape of the sampling distribution will automatically be normal. We also said if the shape of the population is not normal, so anything else weird, the shape of the sampling distribution will be normal if the sample size is greater than or equal to 30. Okay, so I have 3 bullet points here. The first one I'm going to say is the shape is normal if both population distributions are normal. Okay, would it make sense to you guys that if it says normal in the problem for both things, then it would be normal? Okay. Normal if both sample sizes are greater than or equal to 30. And what you write is CLT applies, central limit theorem. Okay, and then there's a third possibility. So since there's 2 of them, there's 3 options. They're either both the populations are normal, both of the sample sizes are large, or one of them is normal and the other one has a sample size that's large. And then what if it's not any of those things? Then sadly, it's not normal and you can't use normal CDF and then it's all bad from there. Yeah, like, yeah, which might be good. You remember back in the day when like you were doing a math 1 type problem and you'd get like a negative under a square root and you'd just write no solution and move on with your life? Yeah, we killed that for you in math too, but this would kind of be like that. You'd just be like, oh, can't do it. Moving on to the next problem. That would be awesome. Probably not going to happen though, because, College Board. Okay. Any questions about this business? Okay. There you go. We just pretend that liquid L is Diet Coke. Yeah, I could go for a large fountain Diet Coke right now. I need all the chemicals to rot my brain, not real sugar. Give me all the aspartame, people. I don't know. I just like diet soda better. And once I got used to diet soda, like the other, it's like heavy. It's like syrup. Like you can't handle it. Okay. Mhm. These are a birthday present, if it helps. Okay. Do you guys need more time? Anybody need more time? Diet soda. Um, yeah, I have problems. Okay, anyway, liquid L, which is definitely Diet Coke, is dispensed from an automatic machine following a normal distribution with mean 27 ounces, delicious ounces, and standard deviation 0.8 ounces. Liquid M, Diet root beer, is dispensed from the same machine following a normal distribution with mean 17 ounces. Oh, that's not nearly enough Diet root beer. And standard deviation 0.5 ounces. 20 random samples of large deliciously, wonderfully bubbly Diet Cokes and 25 random samples of fantastically wonderful Diet Root Beer are chosen. What is the shape of the sampling distribution? Okay, so I'm going to come up here and I see that this says normal and I see that this says normal. So which bullet point does this satisfy of my top bullet points? First one. Okay, so we say normal because both population distributions are normal. Okay, now let's pretend real quick. We're going to do a minor bit of pretend that, first of all, do you guys see that the sample sizes are too small to satisfy the central limit theorem? Okay, well, let's pretend that this one said 30 and this one said 35. And let's pretend it didn't say normal, just like if it was a different question. You would say N1 equals 30, N2 equals 35. 30 is greater than or equal to 30. 35 is greater than or equal to 30. So CLT applies. Okay, do you understand how to answer that question? If it was about CLT. This particular example is not, but if it was, that's how you would answer it. Does that make sense? You sure? Yeah, if it if it didn't say normal and these were bigger numbers, then you would say normal because of this. Oh, then you would just say not normal, and then oh, yeah. And then you just couldn't do the problem. And you'd be like, no solution, moving on with my life. Yeah. But I don't know that it's ever going to do that because, well, okay, this is when you'll see it. You'll see it when it says, like, what's wrong with this one? Why can't you do it? Or something like that. Okay, anyway, find the mean of the sampling distribution. So mean of X bar L minus X bar M. I got these letters from over here, so it's telling you that it's large minus medium. So the large has a mean of 27 and the medium has a mean of 17. So 27 minus 17 is 10 ounces. Good so far? This 7.5. It's the baby one. Oh yeah, it's like the big gulp size. Yeah. Okay. Calculate and interpret the standard deviation of the sampling distribution. Verify the 10% condition is met. Okay, so we're going to start with that, of course. You guys think that that machine probably has more than 200 drinks come out of it? Sure. And I think it's safe to say there's 250 medium drinks or more. Oh man, I didn't leave myself much room for the interpret. It's fine. I'll just cram it in. Okay, so formula says the first standard deviation squared, which is 0.8 squared over the first sample size plus the second standard deviation squared over that sample size. I didn't put any parentheses or anything. It's not required. Don't need it. Just type it in how it looks. Can you guys please focus? Please. 0.205. Anybody know what kind of question is left? We've been doing the same exact thing for days. What kind of question is the last one gonna be? Probability, normal CDF. Yeah, yeah, yeah. Okay. Great, great. You're picking it up. You're getting the pattern. Wonderful. Okay, there's a couple of little things here. So first, we know we need normal CDF. I'm gonna put it over here on purpose. Okay, what things do we need for normal CDF? Yep, low, high, mean, standard deviation. Okay, we're gonna put the low here. We're gonna put the high here. We know the mean is 10 from the previous problem. And we know the standard deviation is 0.205 from the previous problem. Do you guys know where I got those from? From problems B and C that we just did on the previous side of the paper. Okay, now this says within 0.25 ounces of the true difference in means. The true difference in means was 10. We got that. And within means plus or minus. So whenever you see that within, you got to make that 10 plus or minus 0.25. So that means that my low is going to be 9.75 and my high is going to be 10.25. Do you guys see where I got that from? And then you write it like a compound inequality at the front. 0.7777777. All I see is a winning slot machine when I see 777.